As we wrap up 4.3, I want to discuss both Pythagorean identities, since we've had a chance to talk about some of the trigonometric identities, and then do some word problems involving trigonometric functions involving angles of elevation and depression. So let's start with the Pythagorean identity. We know oftentimes the popular formula with the Pythagorean theorem is a squared plus b squared is equal to c squared. And if we know that our hypotenuse is 1, we can then say x squared plus y squared is equal to 1. And I bring that up because when we were working with triangles that we draw on the Cartesian plane involving the unit circle, we have a hypotenuse of 1. Let me actually just go closer to here. So if we can say this, we have said so far that the cosine of an angle that is within the unit circle corresponds to the x value. So we can replace x with cosine of theta. And I want to be really careful here. Notice I've put parentheses around my trig function to indicate that I am squaring the entire value of cosine theta. And that can get a little annoying. So what mathematicians also agreeing with you, and that can be a little bit annoying, said instead of writing the parentheses every single time, we can actually just write cosine squared theta. This is equivalent to cosine theta squared. And just to be clear, this is not the same as cosine theta squared. So we've got to be really careful. It's a very small notation thing, but we're saying different things here. So we have that. We replaced x with cosine theta, which allows us to write cosine theta squared as cosine squared theta. And we know that y is equivalent to sine of theta, so we can then say this is sine squared theta. And so this is our Pythagorean identity for trigonometric functions. Okay, so there's a trigonometric Pythagorean identity, which says that cosine squared theta plus sine squared theta is equal to 1. And again, what makes this an identity is that this equation is going to be true for any value of theta. For any angle that we plug in, this statement is true. Let's say, for example, that theta were equal to pi over 6, for example. Well, cosine of pi over 6 is root 3 over 2, so I'm going to square that. Sine of pi over 6 is 1/2, square that. Is that indeed equal to 1? Well, yeah, that gives me 3/4 plus 1/4, and that indeed equals 1, okay? So that's the idea of the trigonometric Pythagorean identity. And there are other couple of versions or corollaries of that. If I took this same identity, which let me just copy this. If I take the same identity, can't speak right now, and I divided everything by cosine squared theta, notice it's the same identity, but I'm just dividing everything by a term. This gives me 1 plus sine over cosine is tangent, so this is tangent squared theta, and 1 over cosine is secant, so I can write this as secant squared theta. So this is one of the other identities, okay? And the last version of that is if I were to take that same Pythagorean identity we've been working with, and this time divide everything by sine squared theta, well, this is going to give me cotangent squared theta, just the reciprocal of tangent. Sine squared theta divided by itself is 1, and 1 over sine squared theta is cosecant squared theta. So here we have this identity, okay? So here are the three Pythagorean identities for trigonometric functions. We're not going to do too much with this in this chapter, but it's a good idea to be aware of them as we are going forward and we start talking more and more about different trigonometric identities. Okay, all right. So before we dive into some of the word problems, let me break down the idea of an angle of elevation and the angle of depression. So let me actually move down here. So this line that we have here, we're going to call this our horizontal. It's a line that's effectively parallel to the ground, or just perpendicular to the y-axis, or perpendicular to the vertical. An angle of elevation refers to the angle that opens away from the horizontal. So this would be an angle of elevation. An angle that dips below the x-axis, we call this an angle of depression. Okay, so we're talking about angles of elevation, angles of depression, and this simply refers to the angle or the amount of angular change from the horizontal line. Okay, so just keep this in mind as we do some future problems in this chapter, but I did want to at least get that established from at this point. So now let's go through a couple of problems here. All right, so you're standing 200 yards from a river, so this is you. And rather than walking directly to the river, you notice someone cute and walk 400 yards along a straight path to the river's edge. This is the cute person right over here. Okay. Find the acute angle. I pause there. Thank you very much. Between this path and the river's edge. Okay. So, given what we have here, we clearly see that we are working with a triangle, right? So I'm just going to draw this here, just outline this. We see that we have a right triangle. Okay, so we see the right triangle. And we know this side, and we know this side here. So given that, which trig function would make the most sense to use from this angle's perspective? We've got the opposite, the hypotenuse, so it would make the most sense to use the sine. We would say that the sine of theta is equal to the opposite, which in this case is 200, over the hypotenuse, which is 400. And we can rewrite this as sine of theta is equal to 1/2. So then what is theta? Well, some of you may be thinking, well, I can use inverse trig functions. I could say that the theta is equal to the inverse sine or the arc sine of 1/2. And you could do that, but we're not quite there yet. We'll actually talk about inverse trig functions a little bit more later, a little later in the chapter. Hopefully you're looking at this and you might be asking yourself, wait, I do know the angle. When I take the sine of it, I get 1/2. Excuse me. The sine of 30 degrees. Theta would have to be equal to 30 degrees. And if you look at this carefully here, you see that, yeah, this is indeed a 30, 60, 90 triangle because my hypotenuse is twice as long as my opposite side. So that would have to be a 30, 60, 90 triangle. Okay? All right, let's try another problem. Go ahead and pause the video right now and work through this public library problem. And hopefully what you found is you should be able to draw a quick sketch. And that's a horrible square. Let's try that again. That's not any better. And I'm trying to see this if it can there we go. So here's my square, which is going to represent my library. I'm going to draw my flag here. Okay, there's my flagpole. And I'm told that I'm standing, or there's a point that's 40 feet in front of the library. So I'm going to just draw this here. This is 40 feet. And the angle of elevation from that point to the bottom of the flagpole, this is going to be 45 degrees. And then the angle of elevation from that same point to the top of the flagpole, well, this is going to be 60 degrees. And we're going to assume that this is a right angle here. Well, what we're concerned with finding is the height of the library here, which I'll indicate as L, as well as the height of the flagpole here, which I'll call F. I'll just say lowercase f there. Well, given what we know about how far we are from the library, as well as these angles of elevation, can we find these two heights? And I'm going to set this up using trigonometry. And those of you who are looking at this right now probably have determined that you could actually do this without any trigonometry whatsoever. And that's because I've used pretty easy angles of 45 and 60 degrees. That is to say, that I've chosen angles that are in the unit circle that we're accustomed to working with. But I want to make sure that we know how to do this with trigonometry in the event that we did a similar problem or future problems with angles like 47 degrees or 62.5, that we could still set it up the same way. All right, so if I could highlight real quick this particular triangle here, if I just highlight this triangle, this right triangle that we've drawn here, which sides would make the most sense if I'm trying to find L? I can say the tangent of 45 degrees is equal to L over 40. So L then would have to be 40 times the tangent of 45 degrees, which we know. What is the tangent of 45 degrees? Well, this is just equal to 1. This is equal to 1. So then we can say that the library's height is just 40 feet. Okay? Well, what about now this triangle over here, this right triangle here? Well, here we can then say the tangent of 60 degrees, setting it up the same way, is equal to L over 40. So then L is equal to 40 times the tangent of 60, which is root 3 over 2. Oh, excuse me, not root 3 over 2, root 3. So L is just equal to 40 root 3. So, excuse me, this is not L, I apologize. This was all done with F, the height of the flagpole, plus L. There we go. All right, so this is referring to this entire height, which is the height of the flagpole plus L. This is F plus L. So if that is the case, if I know that the height of the flagpole plus the height of the library is 40 root 3, that means 40 root 3 minus 40 feet has to be the height of the flagpole, which in this case turns out to be approximately 29.28 feet. Okay. Well, how could I do this problem without using any trigonometry? Well, hopefully if you looked at our triangles carefully, you saw that our blue triangle was 45 degrees, 90, which makes this a 45-degree triangle, which means because this is a 45, 45, 90 special right triangle, or just basically an isosceles, I know that this library's height has to be 40. And in the same way, if I'm looking at my red triangle and I see that that angle is 60 degrees and this angle is 30 degrees, this entire F plus L height had to be 40 root 3, okay? All right, final question. Go ahead and pause the video and give this one a go. And hopefully you're appreciating the tree that I've drawn there. If I draw a height or distance of 50 feet from the base of the tree, and I know that my angle of elevation here is 71.5 degrees, and I'm trying to find the height of the tree, it would make the most sense to use tangent. The tangent of 71.5 is equal to h over 50. H then is equal to 50 times the tangent of 71.5 degrees, which is approximately 149.43 feet. Okay? All right. So hopefully you understand angles of elevation a little bit better now, and we can see how we can use trigonometric functions to solve some application problems and using those.